Okay, now continuing on with our discussion on sine and cosine, let's look at this diagram here. I show the x-axis going off on this direction, and then the y-axis is the vertical axis right in here. And here I show a line segment of length 1. Okay, and say that the angle made with the x-axis, here I'll use x. I'll say the angle is x instead of theta. So I'm using a different symbol. If I call this angle x, then I may not want to call this the x-axis because that'll be confusing. So how about if I call this the v-axis, okay, right in here. So that's the v-axis instead of the x-axis, and I call this angle here x. Now the sine of x, the sine of x is equal to the projection of this line right here onto the y-axis. In other words, it's equal to this right here, this projection onto the y-axis, okay? So this would be then the sine of x, this point right here. Now notice as the angle x here is small, so if our line segment looks like this, okay, and the angle x then is this small angle right in here, that the projection, so this would be the angle x right in here, the projection onto the y-axis is also small. It's only this distance right in here, right? So if the angle x is larger, like it is with the red line, the projection on the y-axis is larger, and it makes the value of sine x larger. When the angle of x is small, like it is here, the projection onto the y-axis is smaller, and so sine x is smaller. Now, as what happens now, imagine as what happens as this line segment will rotate around like this. So as the angle of x gets larger and larger and larger, the line segment will rotate around in this fashion. So for a very, very large angle of x, okay, the line segment's now over here, and this whole thing, let me choose a different tool. This whole thing right in here is what the angle of x is. Okay, this whole thing right in there. So the angle of x goes from here all the way around to here. And after we pass this point, as the line keeps going around, the projection onto the x-axis will get smaller again. And then when the line is all the way around to this point right in here, let me draw it in red, the projection onto the x-axis is 0. Then as the line continues around, we find that the projection onto the x-axis, going all the way over to here, now becomes a negative number. So this becomes a negative, the sign becomes negative. So let me plot for you the value of the sine of x as x increases from 0 on out. So I'm going to do that with this plot right in here. This is y equals sine x. And as you see, the value of the sine starts at 0, and that's what you get when the angle, let me put in another there. So here's my axis. So when the value of the angle is very small, that means it's an angle that looks something like that. The value of sine x is very small. Indeed, when this angle is 0, the sine x just aligns with this axis right here, and the sine of x is 0. So sine x starts out at 0, and as this line segment rotates around, the projection onto the x-axis gets larger and larger. Here you see it getting larger and larger. It reaches a maximum right here when the line segment is going straight up and down. So when the line segment is right here going straight up and down, is when the projection onto the y-axis is at its peak. There, the value of sine x is equal to 1. That's the length of the line segment, 1. Then as the line segment continues to rotate around this way, the value of sine x drops off, drops off, drops off. Then it equals 0 right here. Now, this angle from all the way around there is pi radians. And that's exactly when it equals 0 right here. Then it starts going negative, and then it reaches a peak of negative values right when the line segment is pointing straight down and continues on around. So this is a plot of the value of sine x. In other words, the length of the projection onto the y-axis. So we're constantly doing the projection onto the y-axis, okay? And it's that length of the projection on the y-axis, which is the sine of x. Okay, now I'm going to show you something that you'll learn where it comes from when or if you take a calculus course. And what I want to show you is that it actually works. The way that your calculator might compute the value of the sine of theta is with this function right in here. See this function right in there. So that's how your calculator might compute the value of sine theta. It says sine theta is equal to theta minus theta cubed divided by 3 factorial plus theta to the 5th divided by 5 factorial minus theta to the 7th divided by 7 factorial, and it keeps adding terms on and on and on. Now, the factorial function, you may not know what that factorial function is. So let me tell you what the factorial function is. The factorial function is given by, let's say, 2 factorial. Okay, so 2 factorial is equal to 2 times 1. 3 factorial, and that's the exclamation point, is 3 times 2 times 1. Because I can forget about putting the multiplying the 1 term here, can't I? 4 factorial is equal to 4 times 3 times 2 times 1, and so on. Now, in particular, notice that 1 factorial is equal to 1, and here's something which is not at all obvious from what we've done, is 0 factorial is defined to be also equal to 1. Okay, now that may not make any sense to you, and it comes from a deeper property of the function that gives rise to the factorial function, and I'm not going to try to explain that right now, but I'm telling you, just remember that 0 factorial is defined to be equal to the value 1. So this is what the factorial function is. So we keep taking terms of the form theta to the, let's say, 5th divided by 5 factorial, and theta to the 7th divided by 7 factorial, and so on and so forth. So that is where, that is how your computer actually computes the factorial function. So let me close this, okay, and let me close this. And now let's look at plots of the sine function and of that expansion of terms that the computer uses to compute the sine function. Okay, so the first function I'm plotting here is just simply y equal to sine x. So that's what this looks like right here. And now the first term in that expansion, let me pull it up again for you. The first term in that expansion is y equal to x. Okay, so I have, if sine x would equal x minus x cubed divided by 3 factorial plus x to the 5th, and so on. So first I'm going to look at the first term, then I'm going to look at the first 2 terms, and the first three terms, and so on. So let's look at that. Sorry, it takes me a minute to pull these up. Okay, now the first term will be, if y is equal to sine x, the first term in that approximation is just x. So this is the plot of y equal x. And notice that in this region, for small values of x, x is actually about equal to sine x. Now if I take the first two terms of that of the sum, this is what the first two terms look like. So if I take x minus x cubed divided by 3 factorial, which is just 3 times 2, this is what the first two terms look like. So it's even a better approximation to the sine. Okay, so you see this is even a better approximation to that. Let's take the first three terms in the sum now. Let's look at this. So this is now the plot that has the first three terms in the sum. That's even a better approximation. Now 4 terms is even better, 5 terms is even better, and we get down here to 7 terms. 7 terms gets us very, very close to the value of sine x, as you can see right here. So that is, let me take out the other plots. So this is actually a very good approximation to sine x. You can see it only starts to deviate from the true value as you get way up into this region. So now let's keep that in mind, and this is how a calculator or your computer will actually approximate the value for sine x when you execute that function on your graphing calculator. Okay, so thanks a lot. Talk to you next time.